so let's talk about deserialization vulnerabilities. So real quick, we will attempt to advance slides. Is it not coming through? It's advancing on my screen and it's not advancing up there. All right. Good enough. All right, so a few words about who I am. So I'm a senior software security engineer at Netflix. I work on the platform security team. We build all sorts of cool stuff to make our microservice ecosystem safe. And if you download the slide deck afterwards, you can check out some of the cool projects that we work on. I'm easily findable online if you want to shoot me some questions after the talk. But let's get into it. Let's talk about deserialization vulnerabilities. So first, I'm going to describe what those are so that we're all on the same page. And then I'm going to talk about what a gadget chain is and why I'm spending all my time talking about that. And then finally, I'm going to talk about the new tool I made to find gadget chains. And finally, the good stuff, some new exploits that I discovered with that tool. So first of all, what is a deserialization vulnerability? So in object-oriented languages like Java, data is contained in classes, and classes also contain code. This is object-oriented programming, and it gives you cool stuff like polymorphism. But this leads to a really important side effect when you're talking about deserializing data, which is that if you control the data type, then you also control code that's getting run, because the code is determined by the data type. So what does that actually mean if you're trying to look at something that's vulnerable and then try to exploit that? So here's an example of like a REST endpoints that would be vulnerable in kind of a classic Java program. So you've got some kind of render user endpoint, it's got a post body, and you pass the request body into the object input stream class, you read an object out of there, and whoever wrote this expects the object that you read out to be a user, and it's going to call something like user.render. So the developer has the intent of the person posting a serialized body that represents this user class. And this does nothing interesting. It's totally innocuous. But where you get into a potentially dangerous place is if the application has something like this on the class path as well, a thumbnail user. And in this case, this is maybe a user that has a thumbnail, which is a path to something on disk. And that means that if an attacker can serialize this thumbnail user class and pass it into this post body, then they can read any file off the disk. And so this is what I mean by if an attacker can control your data type, then they might be able to directly influence what code gets executed and potentially do something unintended. So deserialization. That's not a new topic. So this was a really popular topic in 2016. But deserialization vulnerabilities actually go to something way before that. So they first kind of came up around 2006. So Mark Schonenfeld gave a talk at Black Hat where he describes exactly this sort of issue. You can potentially do weird things with your data types in a serialized body and get arbitrary code execution. But this really gained steam in 2015 when Frohoff and Lawrence gave a presentation at AppSec Cali where they showed that there's arbitrary code execution gadget chains in all sorts of open source libraries that are commonly pulled in, like Commons collections. And so if you've got any application doing unsafe deserialization, and that included things like Jenkins and various application containers, then you've got arbitrary code execution on those apps. And it's because there's just so many libraries that have these interesting gadget chains in them that end up doing arbitrary code execution. So the year that followed, I've heard a lot of people refer to as like the Java deserialization apocalypse, because just everyone realized that they were vulnerable to this. And so lots of talks were given in that year. And probably my favorite one was by Luca at an OWASP meetup, where he just did a really good job of outlining this is what a vulnerability is, this is what an exploit looks like, this is how you fix them. So this is a good talk to go look at afterwards if you want to kind of dig a little deeper on what vulnerabilities look like. But the subject didn't end there. So at last year's Black Hat, Muñoz and Miroshis gave a talk about JSON parsing libraries that are also subject to these kind of deserialization attacks. So for a while in 2016, everyone's like, all right, if I just don't use the Java like object input stream, then I'm not going to be subject to these vulnerabilities, so it's all good, right? And the answer is no. There's still plenty of ways other Java deserializers or deserializers in other languages can be vulnerable to these sorts of exploits. So this is a really good survey of all sorts of different deserializing libraries and in lots of languages besides Java. So that's another good talk to go check out. So there was that talk last year. There's this talk right now. So that's the end of the deserialization story, right? No, like this is still an important topic. We still haven't killed off this vulnerability class. So in October this year at AppSec USA, there's still going to be another talk about deserialization and why you shouldn't be doing this in a dangerous way and what can go wrong. So this is still a relevant topic, and it's something that we need to understand more deeply because it's obviously not going away. So what's the deal with Java deserialization vulnerabilities? Why are they so interesting? Why did this cause so much strife when we realized what a big deal they were? You know, if all deserialization vulnerabilities looked like what I had in that first slide, they wouldn't actually be that interesting. The reason they're interesting is because there's these things called magic methods. And those magic methods will get automatically executed by the deserialization library while it's constructing your payload from the serialized byte stream. And that's what gives rise to all sorts of interesting behavior that attackers can exploit. So here's another example of that. So this is the exact same post endpoint as before, but let's say you have this like evil class that's on your class path for some reason. This probably doesn't actually exist anywhere, but for the sake of the example, there's this class implements this read object method, and that's one of these magic methods that gets automatically invoked. And that thing's going to read something out of the object input stream and execute it, so shell out to whatever it read in. And the thing about this magic method, this read object method that's so critical, is that that gets executed before this read object method ever returns on the left-hand side. So it doesn't matter that this evil class can't be cast to a user because this magic method gets invoked before that ever returns. So magic methods, what's the deal with those? Like, you've probably never implemented one. You're just like, how common can these things actually be? And the answer is that they're incredibly common because the JDK has them all over the place. So HashMap is a really good example of a class implementing one of these magic methods. So it implements read object. And the reason that it implements these write object and read object method is because it allows serialized versions of a hash map to be interoperable between different JDK versions. They might want to change the way they manage their hash tables and things between JDK releases. And if they did that and they use default serialization techniques, then those serialized versions of hash maps wouldn't be interoperable. But by instead implementing write object and serializing out the hash map as just a list of key value pairs, they can read that in any version of the JDK as a list of key value pairs and call this.put with that key and that value for each one they read in. That means that as the Java deserialization library is deserializing a hash map, you're calling object.hashcode and object.equals for each of those keys you're reading out of that list. So this gives us a way of getting to other known entry points. So if there's a class that has an interesting hashcode method that does something potentially dangerous in that hashcode, then even though hashcode isn't a magic method, we know we can wrap it inside a hash map and we'll end up invoking it. And that kind of gets you into what gadget chains start looking like. It's where you move from one method that you know the deserialization library will invoke and getting into another one and then potentially more from there. So I talked about HashMap. Priority queue is just another really common example that I've seen attackers use in building up gadget chains. But if you check out a project like Why So Serial, you'll see a bunch of others. So here's an example of how magic methods get you to gadget chain. So this is a really simplified version of what read object looks like in a hash map. And the main thing to notice is that it reads keys and values out of that object input stream and calls hash code on the key. And so if I put into my object input stream something like this class, and this is an example, again, simplified example, but an example of a class that comes out of the closure library, then what this class does when you invoke hash code on it is it looks up inside its map for a I function instance and calls invoke on it. So if I put inside that closure function map an interesting implementation of I function, I can get into a class that does interesting things and invoke. So here's an example of a function implementation that composes two other functions. So let's say for F1, I implement the constant function that just returns some constant value. And for F2, I direct the payload to deserialize an eval function. And that means that I can get some arbitrary value passed into the invoke on function eval and basically get RCE. So this is what a gadget chain looks like in a deserialization exploit. And if you want to know what that would actually look like on the wire, this is an example of a JSON version of that kind of a payload. So you wrap that interesting abstract table model class that had that interesting hash code implementation inside a hash map, and then you just supply as the instances of all those member variables these interesting classes with potentially more interesting member values inside that. So the important thing to note about that example that I just gave, though, is that all of that had nothing to do with what the application was actually calling, what code it was invoking. That payload would have worked just as well with that first example I gave that tried to cast things to users. It had nothing to do, that payload had nothing to do with what the application expects to do with the payload once it's deserialized. Everything that determines what gadget chains you construct is determined by the class path, by what classes exist inside your application. And that doesn't have to be just classes you call directly. That is the cumulative sum of all of your transitive dependencies. So if there's something interesting in some transitive dependency you didn't even know you were pulling in, a deserialization gadget chain can potentially utilize that. And that's what makes these things so dangerous and so prolific in applications and practice. So what Java deserializers are vulnerable to these kind of exploits? So the JDK object input stream is the classic one. That's the one that where all this attention started gaining steam. But that's definitely not the only one. So Xstream is another example of an XML parser where you can specify your data types and therefore end up instantiating arbitrary things and potentially building gadget chain. All of these JSON libraries are potentially exploitable. Some of them are not by default, but with some certain configuration options might end up being exploitable. So you should spend some time reading Muñoz and Miroshis if you're worried about those and understanding exactly how and when those are exploitable. But the point is that there's lots of different libraries, and all those libraries have different ideas about what classes they'll deserialize and what magic methods will be invoked. And so those different libraries might end up having different types of gadget chains possible. And that's something to keep in mind for later. So finding vulnerabilities. How do you actually know if your application is vulnerable to a deserialization bug? Well, finding a potential deserialization vulnerability isn't really any different from finding many other types of application security vulnerabilities like SQL injection or XSS. It's really just a question of, can attacker-controlled data flow into your application and then go into one of these potentially dangerous sinks? In this case, a parser library, a deserializer library, like any of the ones I just named on that last page. And that's basically the same thing as something like SQL injection. Does something attacker controllable flow into a SQL statement? So existing tools are pretty good at finding these kind of vulnerabilities. We understand how to find them statically and dynamically. So I'm actually not that interested in how do you find these things, because that's a topic that we've been discussing for years. It's not where I'm going to focus on. What I'm really interested in are the gadget chains. So why am I interested in gadget chains? And why is that the focus of this talk? And the answer is that it has to do with what do you do with the vulnerability once you discover it. So why not just use a better serialization strategy? Why not use some library or some configuration that isn't vulnerable to this kind of problem? And I think Luca summed this up in his 2016 talk the best. It's 2016. There are better options for serialization. And that was true then. That's true today. But my answer to that is that's fine if you're developing a new application. But what do you do when you're working with existing applications that have existing clients out there in the world where changing the way that you parse their payloads might end up breaking things? So who recognizes this guy on the left? So this is the original Wii DVD that got sent out to customers of Netflix so that they could stream Netflix from their Wii. That thing went out around 2010, and that's got a client stamped on the disk, which if you wanted to go use it, like, we should still understand how to parse payloads from those clients. The thing on the right is in a first generation Roku, also came out around 2010. And there's probably a bunch of those stuffed in someone's closet. And same thing, if you plug that in today, like, that should boot up and be able to stream Netflix, or at the very least be able to talk to some kind of Netflix server and be able to get a firmware update. And we should be able to understand those payloads. So there's plenty of contexts where updating your IPC mechanism is really hard or impossible because you've got clients out there that you can't readily update. And the thing is, even if you're not in one of these contexts, even if you do have full control of both your clients and your servers, it's just an expensive thing to do if you have to go update all your clients. Like, it takes a lot of someone's time to replace an IPC mechanism. So is it worth the effort to remediate one of these vulnerabilities? That's ultimately the question. If it's going to take a developer like 3 weeks of time to go update a server to understand some new protocol, then go update all the clients, make sure they're all really updated, then go take the old one out, is that worth doing? Maybe you've got some vulnerability, but it's not actually exploitable. You can't do anything with it. Oh. So how do you know if your application is exploitable? So there's a few known exploits in a bunch of open source projects. So Serial is probably the most well-known one. And that's run by Frohoff, the same person that started talking about these vulnerabilities in 2015. And that's got a lot of gadget chains that researchers have discovered in open source libraries. So if you look at that project, look at the places where there are known gadget chains, then you can look at your application, determine whether or not it's got one of those libraries, and be like, okay, it's got one of those libraries. I know that that thing's vulnerable and that thing's exploitable. MarshallSec is a similar open source project. So it's got a wider breadth of exploits. It's got some gadget chains for other libraries. But it's kind of the same thing, where it's got a bunch of known gadget chains, but isn't going to tell you anything specific about your application. It's not going to tell you, are there gadget chains that are unique to my random collection of libraries that I happen to have on my class path? And for that matter, neither of these things is going to give you much information if you're using some kind of non-standard deserialization library that these things weren't built around, but which is still potentially dangerous because it instantiates arbitrary object types. So what tools are out there? So I've talked about Serial. Joogle's another interesting project that allows you to programmatically query things about data types on your class path. If you're manually building up a gadget chain one link at a time and you want to know, for example, what are all the implementations of map on my class path, that thing will give you that answer. On the other hand, if there's 5,000 implementations of map on your class path, that's a lot of stuff to then sift through and find out if any of those do anything interesting. There's the Java deserialization scanner. That's a Burp Suite plugin that basically uses payloads from Serial to dynamically scan your app and determine if any of those payloads work. Already mentioned MarshallSec. Earlier this year, the NCC group released a Burp Suite plugin, which again kind of does the same thing as the other Burp Suite plugin, but that one's mainly based on payloads from Muñoz and Miroshis' work at last week's Black Hat. But all of those things don't really do what I just described on the last page. Tell you something that's unique about your application. So really, what is it that I'm after? So we've got thousands of applications in our Netflix microservice ecosystem. And when we stumble upon one of these vulnerabilities, we really want to be able to assess the risk of that vulnerability. We would like to know how important is it to remediate. Is it even exploitable? And if it's exploitable, what kind of exploits are possible? RCE, SSRF? We'd like to know. And so if we're answering that question, we don't necessarily have to be perfect. A reasonable overestimation of risk is still useful. And we don't actually have to generate payloads if our goal is just to understand what gadget chains are possible. What is a good starting point if I was trying to exploit this? So what are the requirements if I'm going to set out to build a tool to solve this problem? Because, like I described, tools exist, but they didn't do exactly what I wanted to do. So really, if I'm not looking for vulnerabilities, I don't have to find them. I'm only going to use this if I already know my application has a vulnerability. But it needs to be able to look at the entire class path, so all the transitive dependencies I'm pulling in, and be able to tell me if there's any kind of gadget chain that potentially utilizes a bunch of those libraries. And it should operate on bytecode so that I don't have to understand Groovy and Clojure and Kotlin and any other JVM language that's been invented in the last few years. And we might even be including proprietary third-party things, which, again, maybe I'm not even using directly, but if it's on the class path, it's potentially usable in a gadget chain. So I really want something that will operate on bytecode inside my application. So that was the goal that I set out to achieve, and in doing so, I created this tool that I call Gadget Inspector. So what it does is exactly what I've just described. It analyzes the bytecodes of your application and its entire class path in an attempt to find gadget chains. So how does it work? Well, it takes in your application, be it in war format or a collection of jars, kind of whatever makes sense for your application, does some analysis, and then spits out what it thinks are possible gadget chains. And the gadget chain here is basically just going to be a link of method invocations where we know that this method can call this one and this one and this one, and then it gets down to something potentially interesting. So let's dig in a little bit to understand exactly what this does and what kind of gadget chains it can produce. So the first step is just to enumerate everything we have on the class paths, and then determine its class hierarchy, what methods override other ones, and things like that. That's not a terribly difficult problem to solve. That's something that you can even do with like plain old Java reflection APIs. But we really want to just enumerate all that stuff because it's going to be really relevant for the next few steps. But something that's really useful to do in this context is if you're analyzing things at the bytecode level as opposed to using Java reflection APIs, is that you can really dig in and understand inner classes, which are the kind of things that end up getting produced when you use some of these JVM languages like Scala or Clojure. So the next step is where things start getting a little bit interesting, where I want to discover what I call pass-through data flow. And the goal of this step is to understand if an attacker is able to control some argument that gets passed into a function, can the attacker control the return value of that method? And we basically just want that so that we can do the next step where we understand what methods call other methods. So that's what we do in this step. And we basically just do a little bit of symbolic execution where we step through the bytecode one instruction at a time, and then whenever we return a value, we will output that. So there's one assumption here that I make in this analysis, which is basically that if any object is tainted, and in this case, I really just, by taint, I mean attacker controllable, then everything about that object is attacker controllable. And that makes sense in this context because in a deserialization vulnerability, if an attacker can control an object, it's because it came out of that payload, so they control everything about that object. There are places where that could break down, don't get me wrong, but for our purposes, it's basically always going to be true. So in this case, we can determine that what this funky syntax in the top right means is that if an attacker can control argument 0, which in this case is the implicit this of the function, then the return value is also attacker controllable. So basically this means the return value is influenced by argument 0. And here we can just see that directly. We're returning this dot value, and if we assume this is tainted, then if we assume every member value is tainted, then this dot value would be tainted. So one more example. Here's something a little bit trickier. It's got an if-else in it, but it's either just returning the argument as passed in or calling function.invoke on some other argument. And this gets us to the next assumption that I make in the course of this analysis. And this is something that makes the analysis super easy. If you are interested in static analysis or symbolic execution or something, determining what branch conditions are satisfiable tends to be the hardest problem. We sidestep that entirely and just assume that any branch condition is satisfiable. This is probably one of the weakest assumptions that I make in the course of this analysis, but it's also most of the time totally reasonable because in practice, any branch conditions we end up encountering in these methods are influenced by member values and arguments getting passed in, and all of that ends up being attacker controllable because we're in this context where we're deserializing payloads inside of methods of objects that are from that payload. So in general, whenever we want a branch condition to be satisfied, we can usually achieve it. So in this case, we just look at all the different outcomes of that branch condition. So in this case, where we return the argument directly, we see that the first argument goes out into the return value. In the second one, we call f.invoke, and then using the result from the above step, where we see function constants return value is influenced by argument 0, we end up deriving that the return value of that is also potentially attacker controllable from argument 0. So next step, step 3, is basically the exact same thing, but instead of caring about return values, we instead care about what methods get invoked. And the goal there is to build up a call graph of knowing this method invokes that one, because that's how you start building up chains. You want to know when method A calls method B, calls method C, and you want to know when attacker control input flows through all of those. So we basically do exactly the same analysis, but this time we want to know when some argument inputs, like argument 0, flows into the invocation of some function and at what argument index that flows into. So again, some kind of weird funky syntax I just invented for the purpose of this analysis here. But all this means is that argument 0 flows into function invoke at argument 1. And in this case, that's happening literally because we're passing this in as argument 1 to function invoke. And then similarly, we know that the F comes out of that closure map. We know that closure map is controllable if you control the this argument. So we know F is attacker controllable. So F, which is the implicit this, the function invoke, is also attacker controllable. So here's just one more example using that compose function from the previous slide. And basically you just run through exactly the same thing. So argument 1 gets passed in as argument 1 there. F1 gets passed in as argument 0, the implicit this. And then using the last step, knowing that the return value is potentially attacker controllable, we can derive that the return value gets passed in as an attacker controllable value, again, assuming argument 0 is attacker controllable. So this is actually, I feel like, harder to follow on a slide deck like this. If you walk through the codes in the tool, it's actually just you execute bytecode one at a time and do what it says, and then you output when you see a method call. So it's actually kind of easier to follow in detail than at this high level. All right, so step 4, if you're getting a little lost, don't worry. This is completely independent of all the other steps. Step 4 is really simple. We just want to enumerate entry points for gadget chains. And this is basically enumerating entry points using known tricks. And as an example, we know that hash code is an entry point because of what I described on those previous slides. We know we can wrap it in a hash map and therefore get to hash code. So this is one of the other limitations of this analysis, is that it relies on some known tricks. Now, the hash map wrapping with its matching method and calling hash code, we'd actually be able to derive from those method invocations in the previous step. But there's other neat tricks that researchers have come up with, like wrapping things in a dynamic proxy, which gets you into an invocation handler.invoke method that you wouldn't be able to derive from this analysis, because that's sort of built into how the JVM works with these dynamic proxies. So there's definitely, as researchers come up with other clever tricks for entry points into a gadget chain, this tool could be enhanced with and potentially find some more gadget chains. But that's all this does. It basically looks at method signatures and it's like, I know that's an entry point. All right, so the last step is just putting it all together. We have this graph call. We have this call graph of method invocations and what methods invoke other ones. We have entry points. So literally all we do now is a breadth-first search through this call graph, starting at these entry points, and output a gadget chain when we reach an interesting method. So let's just walk through this, basically coming up with that gadget chain I had from one of the first slides. So we have this starting point, and then we have all those method invocations there where we call function.invoke and pass in argument 1 or argument 0. And so the next assumption I make here is that we can jump to any method implementation we choose as long as it's in a serializable class. And again, this is just because we're in this context where an attacker controls all of these methods and what class gets instantiated as one of those member values. So this is literally how you construct those gadget chains, which is the attacker specifies what class type you should supply as these members. So when we enumerate all the different places we can go to in this graph, we choose every implementation to start our graph search. So as an example, using that method call, we might include function compose.invoke as one particular implementation. You look at all the things that invokes, and as we are walking through this, we say, all right, well, we might choose the eval function as the implementation we invoke here, and then inside that eval function, we know that it calls runtime exec, and then you end up with this gadget chain. Because we know runtime exec is interesting, you can invoke arbitrary code with it. So this is how the tool ends up outputting a bunch of gadget chains it discovers from the class path. So the last limitation that I'll describe is that it relies on some known interesting sinks. So obviously runtime exec is one we know about, and there's a whole list of other interesting ones that have been built into Gadget Inspector. So things like opening files, writing files, opening URLs, doing DNS lookups, terminating the JVM. Lots of interesting sinks that exist in there, but it's entirely possible that I've missed some more interesting things, so just enumerating more of those could also potentially find some more gadget chains. So in everything I've described, one thing that I've left out is how do you deal with this if you're working with different types of deserialization libraries? Well, basically everything I've described is parameterizable. So what classes are considered serializable? Well, you can pass that in as a parameter to this analysis and say classes implementing this interface are serializable, or classes with no arg constructors are serializable, and that'll determine how you do that graph search in step 5. Different deserialization sources exist, different matching methods between different libraries. Again, parameterizable in step 4. And what method implementation should you consider for things like the JRE, object input stream? That's basically any implementation you want, but for something like Jackson, there's annotations you can put on methods that determine what data types can be used for those member values. So it depends, and all of that's parameterizable in this analysis, though. So, all right, lots of talk about lots of things that this tool does, and lots of assumptions that it makes. So the question is, does it actually find anything useful, or is it just false positive heavy and totally useless? So first thing I did was set out to scan some open source libraries and see what it comes up with. So ran Gadget Inspector against 100 most popular libraries as listed on mavenrepository.com and looked for exploits against Java deserialization, the built-in object input stream. So it did rediscover several known gadget chains. So that's good. That means it's actually finding things I know it should find. So thumbs up. It's doing something useful. It turns out that not that many open source libraries actually implement classes that implement serializable. It's not that popular these days to use the object input stream, but there were a few new things that fall into that class, so I'm going to talk about those. It did actually find some interesting new stuff. It did have a handful of false positives because there are some assumptions, but there's not that as many as you'd expect. And I think that's because most of those assumptions I made are reasonably valid. They make sense in this context. Most of the sources of false positives is because reflection is hard. So old gadget chains. So Commons collections, this is the big one that Frohoff and Lawrence talked about in 2015. And the reason that this one was so interesting is that it was in Commons collections, which is the 38th most popular library according to Maven repository. And this is basically what the start of that gadget chain looks like. You wrap something in a dynamic proxy, you get into the invocation handler entry point, you go to this lazy map in Commons collections, and then you're able to do some reflection stuff and get somewhere interesting. So, cool. Found the Commons collections gadget chain. It's doing something useful. The very first thing that Gadget Inspector discovered, though, was a gadget chain enclosure. And we thought Commons Collections was interesting because it's the 38th most popular library. Clojure is the 6th most popular library. So this was really interesting to me. So it found a gadget chain starting in hash code and got down to the bottom here where basically it was able to read an arbitrary file from disk and execute it as Clojure. So it turns out that by tweaking that last step, and instead of calling load file, you call eval, you get exactly the gadget chain that I've kind of been describing at the beginning of the talk. So that turned into an RCE gadget chain. It's been in all versions of Clojure since like 1.2.0, which is like 8 years old or something. And I reported that to the Clojure dev mailing list, and they decided to just turn off serialization for this class, because like, who in the world even uses that anyway? So that's great. Version 1.9.0 release doesn't have that gadget chain anymore. So, cool, progress. All right, what else did Gadget Inspector find? So it found stuff in Scala. So that's the 3rd most popular library on mavenrepository.com. So this one isn't RCE, so maybe a little bit less interesting to you, but it is able to write out a 0-byte file. Why is that interesting? Well, it lets you overwrite a file with 0 bytes, which can potentially cause some denial of service. If you overwrite your application resources, that could then just crash your application. So that's kind of interesting. It also found just a slight variation on that gadget chain where it will do an SSRF, so a get at an arbitrary URL with your application. So cool, it's finding useful stuff. All right, just before I put these slides together, I reran the analysis on Clojure. It turns out that there's actually a different entry point that gives you exactly the same gadget chain. So even though they removed that gadget chain in 1.9.0, it turns out there's still actually an RCE gadget chain in all versions released since then. So I haven't actually followed up with the Clojure dev mailing list, but it turns out if you've got an application that's doing unsafe deserialization and you've got the 6th most popular library on your class path, then there's an RCE in there. So yeah, hopefully this is just reiterating the fact that you've got to stop doing unsafe deserialization. Okay, so that's all great. It proved that Gadget Inspector is doing something useful for open source libraries. But the whole point of this was to be able to tell me about the risk of my applications. I wanted to know whether or not there's some gadget chain that's unique to my app under some unique constraints about the deserialization that I'm doing. So first app that I looked at was an app that was doing some unsafe deserialization with JSON, where an attacker could specify what class we're deserializing and the whole payload. So because we're using JSON in its default configuration, it can only deserialize classes with no R constructors, and the only entry points are going to be those constructors. But there's a 200 megabyte class path on this app, so maybe there's something there. Like, we spent a little while looking at it manually, and we couldn't decide, but it's like, this is kind of icky. Like, we don't know if there's some random constructor out there that does something interesting. So I ran Gadget Inspector. It didn't find anything. So, all right, cool. Maybe we don't actually need to worry about this. So that's a good lesson in how this saved us some time. We didn't spend that much time remediating it. Its priority dropped down. We eventually fixed it, but it wasn't something where we had to drop everything and fix this before we could get out some more features. But, of course, I'm not going to leave you with that. Let's get to something more interesting. So there was a second web app which was using a non-standard deserialization library where an attacker could specify what data types to deserialize, but it had some really weird and interesting constraints on it. It didn't use the read object magic methods, but it did use read resolve. Serialized objects didn't need to implement serializable, but they did have a bunch of other restrictions. So it couldn't have any member fields with dollars in the name. It couldn't have any arrays or generic maps as members. And it couldn't have any null member values. And that was the kicker, because it means that if it had some value that was like a character array or a byte array or something, then it wasn't serializable by this library because that couldn't be null, and this doesn't support serializing arrays. So it was hard to tell, for that matter, what classes on our class path were even serializable. And because there are no null values, this is a recursive requirement. All of its member types also had to satisfy these restrictions. So it was hard to tell what was even serializable in this case, much less whether or not gadget chains existed. But it found something. So this gadget chain is 12 steps deep. And, don't look at exactly what the different methods are, because that's not nearly as interesting. It's just a fact of what the different packages are. So there are 7 different libraries involved in this gadget chain, including classes in the app itself and some JRE classes. So this is something where just looking at a project like YSO Serial or Marshall Tech wouldn't have been able to tell you that there's a gadget chain that exists when you have this random collection of classes in your class path, plus some behavior that's unique to classes in your app. And so this was incredibly cool. And what this gadget chain does is it copies a file from an arbitrary location to an arbitrary location. So what we were able to do with this is copy private keys into the web app resource directory and exfiltrate secrets off of that box. But a few minutes of manually inspecting this after the fact, what you realize is that there's this stream pumper thing at line 8, which basically copies an input stream to an output stream. So there's a small tweak you can do on this where you specify a arbitrary string as your input stream, and then an arbitrary file path as your output stream, and now I can write arbitrary string to a JSP file and get RCE with this gadget chain. So this was even worse than what Gadget Inspector originally thought it was. And so that's amazing. This thing was able to tell us in the course of a few minutes that there was an RCE gadget chain in this app. So that is a huge win. So there's lots of room for improvement with this tool. It chokes on reflection a little bit. I talked about the assumptions that it makes. I talked about the limitations that exist with knowing about different sources and different sinks. But one of the things that I really think is worth taking away from this is that I think it's completely uncharted territory for the deserialization space, automatically finding these gadget chains. And I feel like it's proven, just in this sort of proof of concept that I've built, that it's able to find some really useful things. And, as I mentioned at the beginning, going through the history of deserialization vulnerabilities, they're not going away yet. There's still things we have to deal with, and we're still realizing that there's new libraries that are subject to these kind of vulnerabilities. So, and hopefully, as that last example showed, the gadget chains that we're able to build for these sorts of vulnerabilities are getting more and more complicated and more sophisticated. So I think we need better tools that are better able to understand our risk profile in these sorts of applications. So this tool is open source. I just pushed it to GitHub, so take a look at it. Feel free to submit PRs. Feel free to just take the ideas and build something robust. But hopefully I just hope that people come away looking at this and using these ideas to improve the state of the world when it comes to deserialization vulnerabilities. So hit me up online if you want afterwards, and that's all I've got. Thank you. Okay. Thank you.